This video is on chapter 24, trigonometric functions. And here what I'm going to do is I'm going to focus on sine and cosine. And we're going to look at example 209 and talk about theorem 210 at the same time. And so example 209, we are graphing three functions. Y equals sine x, y equals 3 times sine x, y equals 3 times sine 2x, and y equals 3 times sine 2x minus pi. And so we're going to use our transformations that we learned in chapter 14 to graph these three functions. Our parent function is sine x. So the graph of y equals sine x is given in the notes. You can see that my computer draws better than I do. But the period here is 2 pi. What that means is every 2 pi units, sine does everything that it's going to do. So if you pick any number and you add 2 pi to that number, the function value is the same. So we start here, add 2 pi, we're back here, the two function values are the same. Function value at 0, function value at 2 pi are the same. Function value at negative pi over 2, function value at 3 pi over 2, they're the same. So the period of sine and cosine are both 2 pi. So that's going to be the same for secant and cosecant as well, since they're just the reciprocals of sine and cosine. Okay, so we look at y equals sine x. What did we learn in chapter 14 about y equals 3 sine x? That's a vertical stretch by a factor of 3. So now, instead of coming up to 1 and down to negative 1, the bounds of sine, we multiply by 3. So now our function comes up to 3 and down to negative 3. This is a vertical stretch by a factor of 3. The period is still 2 pi. It still does everything it's going to do in a range of 2 pi units. It's just stretched. What did we do for part B? We added a horizontal compression to this. So the 3 is still our vertical stretch by a factor of 3. So we go still down to negative 3 and up to 3. But multiplying by 2 inside the function, this is a horizontal compression by a factor of 2. And so now what happens, we take this function and we compress it by a factor of 2. And that's what's happened here. So if you look, you see 0, pi over 2, pi, 3 pi over 2, 2 pi. We have these. We have 0, pi over 4, pi over 2, 3 pi over 4, pi. And you'll see that we shorten the period from 2 pi to pi. This function does everything it's going to do over an interval of length pi. So from 0 to pi, it takes on its entire range, and after that it just repeats. So this is the graph of y equals 3 sine 2x. What do we do here? We're going to add a horizontal shift to this. We still have our vertical stretch by a factor of 3. We still have our horizontal compression by a factor of 2, but now we have a shift right of pi over 2 units. So we can take this function and rewrite it this way. So if we factor a 2 out of this 2x minus pi, we have x minus pi over 2. So this shifts our graph right pi over 2 units. So we still, from negative 3 up to 3, the period is still pi. We still have our horizontal compression by a factor of 2. But now we've shifted it pi over 2 units to the right. So if you look at this graph here from 0 to pi, you see what it does? Now start at pi over 2. It does the same thing. From pi over 2 to 3 pi over 2. So we're just starting here instead of at 0. So this is a shift right pi over 2 units. And so sine and cosine behave this way. If you look at theorem 210, the absolute value of 3, which in this case is 3, but if you multiply on the outside by some number a, then the amplitude is absolute value of a. So the amplitude here is 3. The next one we looked at is period. The period is 2 pi divided by b. So here our b is 1. And here our b is 1. So for these functions, the period is 2 pi. Here b is 2, and in the second one, or in part C, b is also 2. So here the period is 2 pi divided by 2, which is pi. And here the period is 2 pi divided by 2, which is pi. The phase shift is absolute value of c divided by b. So here the phase shift is going to be pi over 2. Absolute value of c, which is pi, divided by b, which is 2. So the phase shift is pi over 2. And again, the shift might be left and it might be right, depending on this sign. In this case, we were subtracting, so our shift was right. If we were adding, the shift would be left. And then finally, the average value of f is d. In all 4 of these examples, all 4 of these graphs, d is 0. So we did not have a vertical shift here. We did not shift this graph up or down in any of these. If you shift it up or down, that vertical shift is going to be the average value of the function. So in other words, if we took this and we shifted it up 1 unit, you see how this goes down to -3, up to 3, down to -3, up to 3. 0 is right in the middle between -3 and 3. If you shifted this up 1 unit, then we would go from -2 up to 4, and 1 would be the average between -2 and 4. And so 1 would be right in the middle. But we did not do a vertical shift on any of these. The other thing about horizontal and vertical shifts and compressions is what we do outside the function generally affects it vertically and intuitively. In other words, you multiply by a number greater than 1, that stretches it. You multiply by a number between 0 and 1, that compresses it on the outside. You add 1 on the outside, which we didn't do, but I just talked about, that shifts it up if you're adding, and it shifts it down if you're subtracting. So if we took this function and subtracted 1 on the outside, that would shift it down 1 unit. So then our function would go from -4 to +2. What you do on the outside generally affects it vertically and intuitively. What you do inside the function affects it horizontally and somewhat counterintuitively. So you multiply by 2 inside the function, that is a horizontal stretch or compression. If your number is larger than 1, it's a compression. If your number is between 0 and 1, then it's a stretch. And we subtract, that shifts it to the right as opposed to the left. So what we do inside affects it horizontally and perhaps the opposite of what we would think, because we're subtracting pi over 2 and we might think, well, that shifts left, but it shifts right. So what you do inside the function affects it horizontally and counterintuitively. What we do on the outside of the function affects it vertically and intuitively.